So welcome guys back again to another video. In this video we are going to talk about the Jablonski diagram and how you can interpret this diagram based on the photochemistry knowledge we have. So this is our second video in our photochemistry video series. If you have not watched our previous video, in that which we have talked about the basic concept of photochemistry and what the photochemistry means, what are the processes, likewise the fundamental things. So I highly recommend you to go back and watch it. If you have the knowledge on this basic concept, it's completely fine. You can follow up from here. Now here I have drawn the energy levels, right? Electronic energy levels. We have ground state, singlet ground state, right, and singlet excited states, triplet excited states, and here from the red lines I have represented the vibrational states, right? You know, every electronic state contains a sub energy levels, right? Vibrationals and rotationals. So I have represented only vibrational energy levels. Now you need to know processes which involves in this photochemical irradiations. As an example, which we have talked about in our previous video, the transition between the singlet excited state to triplet excited state. So let's say you are having a molecule which is on the excited state, it will go to the triplet excited state. Okay, what's the process which we are calling this? We calling this as intersystem crossing, right? This is we are calling as intersystem crossing. And also, you know, when excitation happens, right, it just not only go to the first excited state, right? It can go up to infinite number of excited states based on the energy they have. Now let's say you have this A molecule which is on the ground state. Now it has absorbed energy. Now it has gone up to this high energy level. Only problem with this transition is these higher energy levels are much more unstable. So the lifetime of theirs are very slow. So this lifetime, this very low lifetime is not enough to go through a photochemical reaction. So what happens is, as soon as they get energy, they will try a way to give up their energy and be stabilized. Now let's say your this S2 state, the molecule is relaxed back to the following stable the next state. Okay, this transition we call as internal conversion. Okay, we call this as internal conversion. And another thing, now you know from our basic spectroscopic knowledge, the direct transition between S0 to T1 is forbidden, right? Because there is a spin change between the S0 to T1. So we call it as forbidden transition. But when it comes to practical aspects, right? When it comes to practical aspect, there is a small fraction of molecule which is transiting from S0 to T1. As well as when molecule has occupied the T1 state, they will relax to the ground state through this direct transition. Okay, so theoretically these are forbidden, right? Theoretically these are forbidden. But when it comes to the practical aspect, there's a fraction of molecules which are going from this to this. Right? Now this process, this relaxation process, we call as phosphorescence. Okay, we call this as phosphorescence. And now let's talk about a most famous process, which is fluorescence. Now what's the fluorescence means? Let's talk about this fluorescence. This is a very interesting topic, right? Fluorescence. This is a very interesting topic. Now what happens is, let's say you have a molecule. Here we have the S0 ground state and here we have this one excited state. Let's draw some vibrational states. Now a transition would be happen. Okay, transition will happen, let's say from ground state to excited state. Now in this transition, let's say you have changed your vibration state to, in here you have the vibration state of 0. Now here let's say you have vibration state of like 3. Okay, the transition would happen to that. Okay, 2 up to 3, or let's say 1, which is more acceptable. Let's consider it. Okay, now what happens in this fluorescence is, after this absorption and excitation happens, you know that molecule has now high energy. Molecule has a high energy. It will try to find a way to be more stable by releasing the energy. So when the relaxation happens, first step, they will undergo a vibrational relaxation. Okay? They will come to the lowest possible vibrational state. Okay, they will come to the lowest possible vibration state, and then they will release the energy to come back to the ground state. So this is the process of fluorescence. Okay, this is the process of fluorescence. So this initial relaxation through the vibration state, we call it as vibrational relaxation. Okay, vibrational relaxation. Now a thing you need to understand about this, most common problems which are very popular in exams is about this fluorescence. Okay, let's say this absorption energy is E absorb and emission energy is E emit. So if I ask you what the relationship between this E abs and E emit, you must be able to tell that E absorption is larger than the E emission, right? It's observable, right? It's easy. If we want to relate this into a frequencies, same, right? Because the frequency and energy are related parallelly. Emission. What about the wavelengths, lambda? When it comes to lambda values, you know, it's opposite. Because if you know the relationship between the frequency and lambda, right, it's opposite to each other, right? So basically, when you are increasing the frequency, you are basically decreasing the lambda or wavelength. Now this is the relationship which we want to get, okay, for this particular graph. Let's draw the graph of absorption. This is the absorption and emission in the same coordinates. So this is the absorption graph, absorption spectrum, and this is the emission spectrum of this particular molecule. Now you will see there is a deviation from the absorption to emission. Okay, there's a deviation from absorption to emission. So this is the lambda. Let's put this one as lambda 1 and lambda 2. So my question is, what is the lambda 1 and what is the lambda 2? In this case, it's pretty much obvious, right? So this lambda 1 means the absorption of here, this guy. Lambda 2 means this guy. Okay, so what's the real thing is, you must be able to explain the deviation between this lambda 1 and lambda 2, or otherwise the lambda absorption and lambda emission. Okay, that's the tricky part. So you need to understand the concept behind it. So you need to mention, like, when the absorption and emission happens, there's an energy deviation. Okay, there's an energy deviation. Why? Due to the vibrational relaxation. Okay, this vibrational relaxation, this frequency is not observable so that's why there's a deviation. With this deviation, this shift from each other, we call it as Stokes shift. We call it as Stokes shift. This is very important. This is a very famous question. So I hope you are okay with this fluorescence aspect. Okay, and let me draw it on here. This is the fluorescence. first the absorption happens, so the fluorescence, then the vibrational relaxation, and then energy release up to ground state. And there's another thing, which is the quenching. So we will just introduce the quenching, right? We will talk more about quenching in our later part of the video. So basically quenching is a whole different path, I mean like whole part in photochemistry, right? So we will talk more about quenching in our next videos. For now, what you need to understand is when this fluorescence happens, right? When this fluorescence happens, you know that there will be a emission, right? There will be a emission path. Now when you have a quencher molecule inside your system, what this quencher will do is it will absorb this emission energy, right? It will absorb this emission energy, so which will deviate this shift furthermore. So what the quencher is doing is it will absorb that emission energy from the fluorescence, right? Which the absorption can, this energy absorption can be like partially or fully. It can fully absorb the emitting energy, or it can partially absorb the emitting energy. So this is the quenching. This is the quenching. So we will talk more about this quenching. So in our maybe fourth video, we will talk about more about the quenching, so you will understand the clearly what these quencher molecules do. So it's more important when it comes to selective analysis and stuff, right? So for now, this just an introduction to quenching, right? That's what just quenching do. Okay, so this is basically the concept behind the Jablonski diagram. So I hope you are okay with it. If you have any problem, feel free to comment below. And in our next video, we will talk about more about chromophores and the transitions like pi to pi star transitions, n to pi star transitions, likewise the basics of the structures. Let's talk about that in our next video.